So far, we have a method to compute the equations of motion, which is basically the Euler Lagrange equations. And they look something like this. Where the Lagrange is T minus V, T being the kinetic energy and V is the potential energy. Now, when you write this expression for simple systems like projectile, the equations are L looks very simple, and then you can take the derivatives by hand. But if the system is more complicated, like say a double pendulum or triple pendulum, then you'll see that Lagrange is not amenable to be differentiated by hand. And that's where you might want to do symbolic derivation. So if L is too complex, we need to compute the derivatives using symbolics. Okay. That is, you can now start using Python in a mode where it actually treats x as x, and when you take the derivative of x, it will give you 1, and you do not have to put a numerical value to this. Okay, let's sort of review symbolic derivatives. So symbolic let's do a simple example, and this will be a hand calculations. So let's say that we have the function f0 equals x squared plus 2x plus 1. And then if you want to find or compute the derivative of f with respect to x, that's simply 2x plus 2. And then if you want to compute the value of df dx at x equals, let's say 1, then it is going to be 2 times 1 plus 2, which is 4. Okay. Now, how would this be done in Python? Okay, it would be something like this. First, we need to import a symbolic toolbox. It's called sympy as let's say sy, and then we say that x needs to be this symbolic value. It's not a numeric value, so we need to say sy dot symbols x real equals true, and we say x real equals true because we don't want x to be complex. Next, we define f0, which is x squared plus 2 times x plus 1, and then to find the derivative, it's simply, let's call it df dx. It's simply sy dot diff. That's telling it to differentiate f0 with respect to x, and now df0 dx has the symbolic value. We need to find its value at x equals 1. For that, what we do is we say df0 dx dot subs x. We need to give it value of 1, and then it'll actually give me the value. So if you want to see it, then you say print. Let's see how this will look in Python. When I first tried to run this program in Windows, I couldn't run it because symbolic Python wasn't installed. So if you run into this problem, when you run this, you don't get an output, and you might want to install sympy to be installed by going to terminal. So name terminal, install Sympy. And once you do that, you install the package and you can do it. So as I said, here we define x as symbolic variable. We compute f0. Here I'm printing f0 to see what it looks like. Then I compute the derivative. I show you what the derivative looks like. Then I take x value equals 1 and then compute the value of the derivative at x equals 1. Let's run this. Control Shift V. So there are a few things going on. First, it prints f0. Then it computes df0 dx, which is 2x plus 2. You can see that's correct. And then if you put x equals 1, the value is 4. And that's what it prints in the last one. And answer is 4. Okay, so once we've done that, now let's do some more stuff. Besides doing this in the symbolic toolbox, sometimes you don't really need to do symbolic calculations. You want to do numerical calculations, and there is a numerical method of computing the derivative. So I'm going to show you what is known as a numerical derivative. So how do you do this? Well, we use what is known as finite differences to do this. So let's say that this is our curve f, and then we have x0 is this point at which we want to compute the derivative. We know that the derivative is basically the tangent to the curve. So what we do here is we compute the value of f at another point x1, which is very close to x0. And once we do that, we can use the definition of the derivative, which is df dx, is basically the difference between f1 and f0 divided by x1 minus x0. So if you can compute the value of f at x1 and x0, then you can use this formula to compute the derivative. Now, x1 should be close to x0. So for example, we typically take x1 equals x0 plus 1 negative 4. Now you can't go too low on that because then your machine precision will affect you and you get garbage values. Okay, so this type of derivative is known as the forward difference, this formula. Forward difference. Similarly, there is something called a central difference, where what we do is instead of taking one point, we take 2 points to compute the derivative. So again, x0 is point which you want to find the compute the derivative. We evaluate the function at 2 points. Let's call that x2 and x1. The value here is f2 and here it's f1. And so my formula for the derivative will look like this. x2 minus x1. So this is known as central difference, and it is known to give slightly better estimates for the derivative compared to forward difference. Okay, again, x1, x2 should be close to x0. So typically we take x1 equals x0 minus 1e negative 4 or negative 5, x2 equals x0 plus 1e negative 5. Okay. So what we'll do now is I will do this computation of the numerical derivative using both these methods and evaluate the function x equals 2, and remember that x equals 1, and remember that x equals 1, the value was 4 for the function. I have imported the symbolic toolbox only to compare the value, since I'm not really using it for the numerical derivative. So again, import sympy as sy. I define x to be symbolic. This is my function f0, and I can print f0 symbolically because I have it defined. Now let's see how to compute the numerical derivative. I compute the value of f0 at 3 points. I compute it at xval. Xval is 1. I computed xval minus part, which will be 1 minus 1 in negative 5. Xval plus part, that gives me 3 values. Now I can compute the forward difference using this formula, f2 minus f0 divided by part, which is this value and this value. Note you could also use f0 minus f1 and give you the same answer. And then central difference, which is using f2 and f1. Okay. So run this, Control Shift V, and you see that the first printf is this function. The second print is the forward difference. It's 4.0001, so we are pretty accurate, maybe up to 5 decimal places. And then central difference with me is just what I wanted. It's 000 all the way. So you can see the central difference is probably more accurate than the forward difference because it's only here, in this case, accurate to 5 decimal places. But central difference seems to be accurate to about 12 places. You know, this is not really true for a more complicated function. More complicated function, you'll have lower accuracies, but in general, central difference beats forward. Okay, now that we have seen how to use the symbolic package in Python, the next thing we want to do is understand how to do chain rule, which will be very important when we compute the derivative using the Lagrange engine. So let's look at the chain rule. Now let's say that our function f, let's say f1, is not just a function of x, what we've seen in the past, but it's x, which is a function of t. Okay, then our goal is to compute df of dt. Okay, so for something like this, you'll have chain rule. And the best way I think of doing this is to actually write the relation in this form. f1 is a function of x, which is a function of t. And so if you want to compute df1 dt, you need to go via x. So I write df1 dx dx dt. Okay, conceptually, you can actually, for example, get rid of the dx and you will end up with df1 dt. That's the rough way of you can think of the intuition behind this formula. So once we have that, we can then compute these individual quantities and we have the answer. So let's do an example. Okay, the example is f1 is sine of x of t. So using the chain rule, so f1 in this case is a function of x, and x is a function of t. So df1 dt is df1 dx dx dt. So df1 dx is the derivative of sine x with respect to x, and then we have dx dt, which you can see is nothing but cosine of x. Dx dt, let's call that x dot. Okay. So you need x dot and the value of x to compute df1 dx. Later on, we'll verify this using symbolic toolbox in Python. Now let's look at another function. What if f function is a function of x and x dot? Okay, then compute the f2 with respect to dt. So here we have f2 is a function of, sorry, I should just put here x of t x dot. So f2 is a function of x and x dot, but x and x dot is a function of t. So here I do the chain rule again. There are two ways I get to t. One is I get from f2 to x to t, and the other pathway is f2 to x dot to t, and I need to write both of those in the chain rule. So the chain rule now is df2 dx dx dt. That is the red. Maybe I should just put it in the red. Dx dt, and then I have plus df2 dx dot dt, and that's my formula for the derivative. Now I can check this with a simple example. Let's assume that f2 x of t and x dot of t. So in order to compute the derivative, I have df2 dt equals df2 dx dx dt plus df2 dx dot dt. df2 dx is x dot, and dx dt is again x dot. df2 dx dot is, when you take this derivative, treat x as a constant, so this will be x, and dx dot dt is x double dot. So the answer to df2 dt is x dot square plus x times x double dot. Let's verify this using. Okay, so import sympy as sy. I need to create symbolic variables for x dot, x double dot, which I have over here, and they correspond to x dot, x double dot that we have shown. It's real equals true because x dot and x double dot are not complex. So that's why we need to do that. So we'll have equations which eventually will have like complex numbers. You don't avoid that. Now f1 is sine of x, my first example. I need to compute the derivative with respect to x, but x in terms of a function of time. So I do the chain rule. So this is the chain rule. Then I have f2, which is x times x dot, in which case I need to break down the two parts. One is with respect to x, one is with respect to x dot, and then I then print the value. So let's run this. Control Shift V. When I run this, I see that the first answer is x dot cosine of x, which is what it is for this. And then for the second one, it is x dot square, which was my first term, and then x times x double dot. So this is how you compute the symbolic derivative with chain rule. Now that we've done all this, let's go back and revisit the projectile example and try to see how to do the projectile example using symbolic derivatives. Okay, so let's write the equations for the, go back to Euler, Lagrange for projectile. Okay, remember we wrote down that d dt is dl dq dot j minus dl dqj equals qj. Here the Lagrange is half mass x dot square plus y dot square minus mgy, and clearly qj is x, y, and then the force was the drag force, fxi, fx Fy, which are the drag force. So in this case, for the Lagrange, we can write the following. The Lagrange is a function of x dot, y dot, which in turn is a function of t. So let's now compute this individual terms. So we have d l d q dot. Okay, so I'll write this as, so let's do that for dl dx dot. Okay. And we'll do the same thing for phi. This will be dl dx dot, and since x dot, and since we are not interested in, there's no real time involved here, we're not computing the other function of time. This remains as it is. You just have to take the expression and differentiate it with respect to x dot, treating everything as constants. There's nothing really, there's no chain rule involved here. Okay. However, if you want to compute this one, which is a function of time, you will have to use the chain rule, okay, because it's a function of time. So here, what we do is we need to, we see that L is a function of x dot, y dot. In that case, L dot, dl dx will also be a function of the same variables. So I'll write this as follows. This will be a function of x dot, y dot. Now, for this particular case, it may not be a function of all these variables, but in general, if you have a more complicated formula, it could potentially be a function of all of them. So here we'll call this as Lx dot. If that is Lx dot, then this derivative will be something like this. dlx dot dx dot. Let's start with x. This is the first variable. X dot plus dlx dot x dot x double dot plus dlx dot dy y dot plus dlx dot dy dot y double dot. So there are 4 terms, and you need to take the derivative of all these 4 terms to compute the chain rule. This is my chain rule. And then the last thing which is left is to compute dl dqj. dl dqj, so in this case x, that will simply be what it is, dl dx, no chain rule, because there's no function of time. So once we have all these pieces, we can compute the equations of motion. So this is done for x here, it needs to be done for y. So I'll show you code which will produce the same equations as we produced previously by hand calculations using symbolic toolbar. So let me open projectile. Okay. So again, import sympy as sy, xy, x dot, y dot, x double dot, y double dot of my symbolic variables. Here I also put in the parameters mass, damping, and gravity as symbolic variables. Now I had a recipe there. The first step in the recipe for computing the equations was find the position velocities. In this case, you don't really need to do anything because they're already defined as symbolic variables, x, y, x dot, y dot. Next, compute the kinetic and potential energy. So half mv square, where v is x dot square plus y dot square. V is the potential energy. To find the then we have the drag force, which is f of x and f of y, which is first given. Now that we have that, we can now write the equations of motion using this chain rule, using d dt of d L dq minus dl dq equals qj. So for that, I did was I computed individual quantities and computed L derivative L with respect to x dot. For the derivative of this term with respect to time, I need to use the chain rule, and this is the chain rule. Okay? And then I find dl dx. So that will give me the first equation. Next, I do the same thing with y, and I get the second equation. And now I can print equation 1, equation 2, and remember that I'm solving for x double dot y double if I put so. This is perhaps much easier to understand. What I did next was I found a way to make this such that you write less code. This might seem like more code, but it becomes simpler once you have multiple equations. In this case, there are 2 equations, but if you have like 5 or 6, then you just have to write a for loop will take care of the chain rule. So I'm going to run this, Control Shift B, and then it produces output, which is the equations using my first method 4a. This is the equations, which you can see looks same as the equations I derived by hand. And then the more efficient way, using loops, it gives me the same equations. Okay. So once you have these equations, they then go in the ODE int, and then you can integrate. And then of course, any